We experience gases all around us in the atmosphere. We sense these gases in terms of wind pressure, artificial wind pressure with us moving fast on a bicycle, temperature, changes in pressure as you go up or down elevation. The main property of gas is that a gas is mostly empty space. This is what distinguishes a gas from a liquid. Gas is mostly empty space with particles moving randomly and rapidly throughout. The density of gas the density of atmosphere is about 1,000 times, roughly 1,000 times less dense than that of water. Since the gas particles are in constant motion, constant random motion, they are fluid, just as liquids are fluid. So they will flow, and they'll flow to even out any gradients. They flow randomly, but that process removes gradients from the system. So if there's a pressure gradient, a gas will create wind. If there's a concentration gradient, a gas will create diffusion until the concentration gradient is gone. This fluid nature means that the gas will fill any shape. It will keep moving until it finds a uniform pressure, uniform mixture throughout. So gases become homogeneous mixtures. And there are exceptions in very still gases where there's a density gradient based on composition of the gas, such as in silos, the decomposition of organic matter can create carbon dioxide. Carbon dioxide has a higher density than the nitrogen and oxygen of air, and it's created at the bottom of the silo, so the diffusion is slow to remove it, so it creates a concentration gradient. Gases change volume. Gases fill the volume, fill the container, so if the volume of the container changes, gases will expand with the increasing container, increasing volume, where they can be compressed with a reducing, decreasing volume. We like to describe the macroscopic properties of gases by the microscopic behavior of the gases. So the large volumes of empty space in gases create low densities, and they allow expansion and compression, because as we change volumes, we're changing the volume of the empty space, not the volume of the gas particles. These molecules are in constant motion. This allows the flow, indefinite shape, and diffusion. When gas molecules collide with each other and with surfaces, they create pressure, and they also carry temperature, carry heat that we measure as temperature. The properties that describe gases overall, regardless of composition, means that we're describing an ideal gas by not needing the composition. Is the amount of gas. We represent that with lowercase n. Pressure of gas, we represent that with capital P. Volume of a gas, or a container holding a gas, we represent that with capital V. Temperature, and this temperature has to be in Kelvin absolute temperature. We represent that with capital T. These four properties are related by the ideal gas law. Pressure times volume is equal to moles times a constant times temperature. PV equals nRT. That R is a proportionality constant, and we call that the ideal gas constant. An ideal gas can be described without composition, without needing to know the composition of the gas. It is described by the ideal gas law. Pressure times volume is equal to moles times constant times temperature. This means that the gas behaves in a consistent and predictable fashion, hence we are able to describe it by a mathematical equation. Real gases deviate from ideal gases at low temperatures and high pressures. Real gases, we need to use the composition of the gas to be able to calculate the properties of the gases. And we describe this ideal gas by the kinetic theory of gases, where gases are made up of very tiny molecules surrounded by empty space. These molecules move in fast and straight lines in random directions. They do not have any attractive forces between each other. When they collide, they have elastic collisions, which means that they exchange energy, but some of the energy does not change. And the temperature of the gas is described by the Kelvin temperature, and this is proportional to the average kinetic energy of the gas molecules.